Following on from our definition of a tree being a graph which is connected and contains no loops and no circuits, we can define a spanning tree to be a subgraph of a given graph, such that if the original graph has nodes V and edges E, the spanning tree has the same set of nodes V and a subset of the set of edges, which we'll call here E prime. So if I start with a set of nodes, which I'll very imaginatively call 1, 2, 3, 4, and guess what? 5. And the set of edges 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, and 2, 5. Then that is a visual representation of my 5-node, 6-edge graph. Fairly clearly, it's not a tree. There's a lot of circuits in there. There's no reason to. There's clearly not a tree. But if I define the subset of edges 1, 3, 1, 4, 2, 4, and 2, 5, then I can see that that is a tree. Now that's not the only spanning tree. There are many other examples of other edges that I could have kept instead of those. But a spanning tree simply has to be a tree in the sense that it's connected, and a tree on the set of nodes of the original graph, V in this case, and avoids any circuits. Now every connected graph, other than a trivial empty graph, every non-empty graph will contain a spanning tree, and usually many different options of spanning tree. So we're only really interested in this subject for finite graphs. It's considerably harder to prove a lot of results in graph theory for infinite graphs, so they're beyond the scope of what we're covering here. Now, we can prove that we can always find a spanning tree in any non-empty connected graph by defining a routine, and we show that that's loop invariant and it stops in finite time. So this is a nice refresher of some of the stuff we did on loop invariance and correctness of code. Our routine for constructing a spanning tree within a graph is as follows. We start by picking any one node of G. And this is a tree. It's the most trivial tree. It's one node, so it can't possibly not be connected. It contains n-1, 1 minus 1 is 0 edges, so it can't possibly contain a loop or a circuit. So basically, this just says pick a starting point. Then my routine says add the nodes of G one at a time, the nodes which I haven't already added, until I have added them all. So this says until the set of nodes in the tree T is the same as the set of all the nodes in G, add a node X from the difference of G and T. So in other words, add a node from G that I haven't already added to T. Now G is connected, so there is a path between each node in T to the new node I'm picking, X. So all I have to do is I have to choose a path such that the path intersects with T at just a single node and add that to T. So what does this mean? If I start off with this graph here, it's a simple graph. There's 6 nodes. There's how many edges? I can't be bothered to count them. It's not a complete graph. There isn't every possible edge. There's no possible edge between 1 and 2 or 3 and 4 in this graph. But what I want to do is I want to look at that which is a connected graph but definitely not a tree. There's cycles, 1 to 3 to 4 to 1 is a cycle. So it's connected, but it's not a tree. So if I choose, say, node 1 to start with, then once I've got node 1 and my first tree is just 1, I need to pick any of the other edges to add now, or pick an edge pick a node which I can connect by an edge. So here I pick node 4, and I choose to have the edge 1, 4 in my tree. Now I pick another node from the original graph, and in this case I pick node 6, and so I draw in the edge 4, 6. I pick another node from the original graph. In this case it's 5, and I've drawn in that edge. Again, once I pick node 3, I can accept that edge, draw that into the tree, and lastly I need to add 2, so I connect that to node 4. So I've created a tree, and it spans all of the nodes of the original graph using only a subset of edges that were in the original graph. Now that isn't unique. For example, at the last stage when I needed to connect node 2 to the graph, I connected 2 to 4, but there was no reason why I couldn't have accepted the edge between 5 and 2 to connect it instead. So it's not unique at all, but that's how I chose to assemble it. So I didn't say there was a unique spanning tree, I just said that there would always be a spanning tree. So what we've shown is that this statement that T is a tree is loop invariant. At every stage of this loop, if I start with a tree and I add a node via a single edge to just a single node, my result is also a tree. So if it's a tree at the start of the loop, it's a tree at the end of the loop. And so G will always stop in a finite number of steps for a finite tree. As I say, the proofs are a bit more complicated if we consider infinite graphs, but we're not doing that. So it'll stop in finite time, producing a spanning tree. We now consider a type of graph where there is a node which we can define as the root, and a tree which contains a root is imaginatively called a rooted tree. And we can describe a lot of relationships between nodes which may represent other properties. For a lot of complex models, like for example a whole class of complex statistical models, are represented by graphical models showing which variables are dependent or independent of others. If I start with a graph here, our definition of roots, if I define one node to be the root, then if I have two nodes U and V which are connected by an edge, if the path from U back to the root goes through V, then we call V the parent and U the child. So because this is a tree, every node will have a parent. They will only have one parent in this situation. The only node which will not have a parent in the tree is the root. So in this situation, visually, U is the child, V is the parent, and R is the root. And again, keeping some fairly obvious analogies going, that I can have more than one node with the same parent, and if those nodes all have the same parent, then they are siblings. And so it looks like a biological family tree, although the way I've drawn it here is the generation sort of going up the page through time rather than down the page, as we would tend to represent a biological family tree. But it's the same structure. So one of the most familiar types of this structure is things like family trees. I mean, particularly family trees, if you look just down, for example, one line, if you look at somebody's father, somebody's father's father, father's father's father, and so on, or the mother's mother. Obviously, situations where you plot both sides, the maternal and the paternal line, it will not be a tree before too long, because you will also get to situations where members of the family tree appear more than once, because even in a fairly mixed breeding situation, so nothing incestuous, but people will eventually have married their 17th cousin 4 times removed or something. So eventually these things will not form trees if you take them in the strictest sense. But again, we can see this visualization of the evolution of humans from other ancestor species forms what mathematically looks like a tree. And this is used to assess things. We can look at the complexity of the tree, we can assess time to most recent common ancestor, and this obviously has a lot of applications in genetics and evolutionary theory.